Hey everybody, welcome to really the first lecture on the concepts of deep learning and algorithm engineering. And my goal for this first couple of lectures is really to give you a broad overview of what's happening in AI and introduce some of the important concepts. And really to impress upon you that we're in an interesting era right now as AI, artificial intelligence, AI is going to impact all of our lives. It's already doing that today and will have an impact on our careers, research, in the future, and to really start giving you the foundational base so that you can take advantage of artificial intelligence, algorithm engineering in your research and your career looking forward. So my goal for the class really is to go through the Bloom's taxonomy of learning, and the first 4 to 6 weeks we're really going to focus on the basics and underlying concepts of neural networks and machine learning, be able to talk the language. It is a new language with a lot of new and interesting concepts, and it's evolving quite quickly. So to be able to keep up with all of that and to introduce that in the first 4 to 6 weeks, you'll be given a project. You all will work on the project individually, and this will be classifying a multi-label problem for cell classification, and we'll do that. We'll introduce that project in detail. It'll be looking at the life cycle of malaria parasite and then classifying the different stages based on the metabolites from the cells, from red blood cells. So, and the parasite itself. So, and then for project 2, my goal is to get you to the point where you can develop and create and produce your own original work. So this will involve getting a database of images and then developing your own feature engineering, which really is how do you organize the data to expose the features so that your model, your machine learning model can work. And the image databases may range from a few hundred images to tens of thousands of images, and we'll explore a few examples before then so that you understand how to manage that and the tools that are available to manage that. But the high-level goal is to get you so that you can create models, deep learning models yourself, and that's the goal of the class. Not to maybe understand every small detail of the mathematics underneath each of these applications or neural nets, but to understand enough of the algorithms, the constraints, the limitations, so that you can implement applications. Okay, so I like to think about the 21st century, the time that we're living in right now is really, it's all about algorithms. Maybe the last 20 years was more about software development and computers and internet, but it looks like the future is really going to be about how we can develop algorithms in narrow applications and then ultimately in general purpose intelligence. So you can think of the Industrial Revolution, basically steam engine from the late 1700s, 1870s, electricity, oil and gas. 1960s probably was the start of the third revolution, if you want to classify it as that, as the communications, electronics, and computers. And then now we're in the internet era. And then on top of all the data that's being created in the internet era is really this opportunity with algorithms. And we're starting to see that today in many spaces. So if we zoomed out and we kind of put this into perspective of human history, modern humans 300,000 years ago to computers just 75 years ago. And if you think about it, only writing was invented in widespread use a few thousand years ago. Well, so that you have some background in the timeline of deep learning is really in the 40s, neural networks were explored. The idea of a perceptron with a single kind of simple inputs to a neuron that mimicked biological neurons in the 50s, and then the implementation of backpropagation and recurring neural networks in the 80s, and then convolutional neural network CNNs, and then the development of standard databases like MNIST. And we'll use MNIST databases. The handwriting database is your first example, has 70,000 images of handwriting numbers from 0 to 9. And that's the hello world of learning, deep learning applications. And then the concept of deep learning, we'll talk about that a little bit more here in just a little bit. And then models such as ImageNet and AlexNet. And these models really are hundreds of megabytes of weights that are part of a neural network architecture with many different layers. And we'll talk about all these concepts in detail. But then, how those models are available so that you can leverage them and then modify them and add to them, something called transfer learning, only within really the last 10 years. So you can go search online right now for AlexNet and download the weights for that and apply that to an image application, and it'll identify thousands of objects in the image itself. The concept of regularization and dropout, we'll talk about that. I have a lecture on that. And then you've seen in your lifetime, IBM Watson, Win Jeopardy, Deep Face, which is a facial recognition from Facebook, AlphaGo, winning one of the most complicated games that are out there in Go, and then BERT from Google, which is a natural language processing. And today we use that often with speaking with or similar algorithms are run for Siri and for Alexa from Amazon and other applications. So quite a long list, but really short period of time.
Psychology is one of the most used skills this week. Would you like to try it?
I mentioned Alexa, and my Alexa went off in my room. So there you go. Alexa, stop.
All right. Norse mythology is one of the most used skills this week.
Alexa, please stop. Thank you. Okay, so I think the important concept to realize here is that we're in an era called artificial narrow intelligence. So we're solving narrow applications with AI. So if we go back to the previous slide, solving chess problems, or solving how to unfold the unfolding of proteins and how to model that. So the AI is being really targeted at specific applications. And over time, the projection is, and then if you have a weekend on the beach, or you're by the pool, or you're at the ski lodge, this is a really good book. You can pick up Superintelligence. It talks about strategies of how to use AI, paths, and potential dangers. And really, its important point is that at some point in the future, there will be artificial general intelligence. And what's the difference between narrow intelligence and general intelligence? General intelligence, you can think of it as a 10-year-old that has general knowledge, can play checkers, can play chess, can learn mathematics, chemistry, all these things, but it has acquired the ability to learn. And then if you have a computer that has the general intelligence of a 10-year-old with all of the compute power and all the data that's available through the internet, that it's only a matter of time before it surpasses the top 1% or all humans' intelligence. So that's the singularity, or a singleton as superintelligence. Nick Bostrom talks about it in his book. And so what time frame could that occur? And if you think about it, well, that seems a little far-fetched. Many human design systems have surpassed nature. And I think flight, airplanes, space travel using aerospace techniques and mechanical designs and rocket fuel are examples of how designs have surpassed nature's ability. So I think that potential is here for artificial intelligence as well. There's a lot of breakthroughs that are required to reach artificial general intelligence. And we're at the beginning phases of those research. One that I can think of is like if you have a model that knows how to identify 1,000 images or more, thousands or more images like AlexNet or ImageNet, how do you combine that with other models so that they integrate easily and then could expand into general knowledge? That technique's not really known today. So what is the time frame for this could occur? Let's talk a little bit more about kind of this definition of narrow AI. Narrow AI performs tasks that are normally required human intelligence, but really in a narrow defined domain. And I think of general AI as it has a general problem solving abilities across many general areas. So it can learn what grocery list I want over time. It can also learn organic chemistry. And if I asked my Alexa today to give me a strategy for Catan, Alexa just points to a website of somebody else documented a strategy. It doesn't, in the background, play the game Catan, develop its own insights and strategies, and report that to you the way a human would. It just, today, what is done is pointing to information that's already been created. General AI will be able to do all of that in a split second in the future, potentially, right? It can go off and formulate a strategy based on games it's playing against itself, learn that, and report back, here's the best strategy to win at Catan. I don't know if you guys know Catan, but my family plays that strategy game at home. It's basically a take over an island with economics, and you have ports, and it's a pretty intense game. So I encourage you to check that out. And if you haven't played it, it's a good game that's come on the market in the last 10 years or so. So, so definition of narrow AI and general AI. So another thing to realize is that if you, this is from the superintelligence book as well, is that, you know, we have AI now that can do very narrow things, and we've done this over 50 or 100 years. But if you think about it, there's not a lot of difference from the brain structure and the abilities between the village idiot and Einstein on a large scale. But if you compare a mouse to a low IQ person, then there's quite a bit of a difference. So we're only talking, you know, the definition from IQ points of 70, 80 IQ points to 200 IQ points for Einstein. But then if you think about it, once you have a computer system that can learn to learn, iterate over time, it's just a short period of time before they could surpass Einstein's insights and ability. So think about that. So the question is, the answer is, will computers ever be as smart as humans? There's probably a very short period of time, and then an explosion in knowledge could occur based on the network systems and data that we have in place today. So that's an interesting concept to think about. So what superintelligence also talks about is that there's a survey of people in the industry, and it says, well, when is this singleton event going to occur? When will we have general intelligence? And 10% of those polled from the academic authors in AI space said, oh, it's going to happen in the next 5 to 10 years. 50% said around 2050, and then 90% said before, let's say, 2075. So that's within our career lifetimes here moving forward. So it's good to understand the potential and the concepts. Now, on the other hand, we may be at the potential peak of the hype cycle, and this is called the Gartner hype cycle. Any technology that's introduced, it creates all this excitement and visibility. If you search on machine learning today, or deep learning or AI, you have all kinds of these analysis and a lot of inflated expectations. Typically, the technology that's introduced goes through this trough of disillusionment. It's like, we can't really do all the things that we thought we could do with this new technology, and it's not going to have the impact that we believed it was going to have. And I believe we're kind of maybe on the other side of the peak of inflated expectations at this point, where the hype about the potential for AI is really overdone. So we can solve these narrow AI problems, and then what happens typically with a technology introduction is that you reach this enlightenment. Oh, these are the constraints. Here's what we can solve today. There's a plateau of productivity, but I think that there is a point in the future where general AI takes place, and we'll see this curve take off. But it's probably years and years out, but it's something to be aware of. So this is where we're at today, is to understand what narrow AI can do, and that's what this class is going to be about, and learning about really deep learning, how to use data and multiple layers of neural networks, hidden layers, to be able to solve problems. So, so what's an example of a narrow AI? Here's one that I've looked at in my undergraduate class that are learning Python. Honors class looks at solving several problems, one of them being melanomas and moles. Can we come up with a system to identify the difference? Well, Google has a model and has worked on this problem extensively. So 1 out of 5 people will be diagnosed eventually with some kind of cutaneous malignancy. So it's a problem that is well known. We have dermatologists that make these predictions. There is a gold standard that we can have the mole or melanoma biopsied and prove to whether or show beyond any reasonable doubt, prove 100% that it's a melanoma or not. So that's an important concept. Is there a gold standard that we can test against? In this case, there is. So 2017, just recently, Google's done some work on skin cancer classification. Look at this. They used nearly 130,000 clinical images and looked at 2,000 different diseases. They used something called a convolutional neural network. We'll use that in our class and talk in depth about that. They started out with using 2 test cases and compared that versus 21 board-certified dermatologists. And they were looking at really a benign case versus a malignant melanoma case versus benign. So they limited and constrained the problem to look at just a couple of applications. Here is an overview of what the architecture would look like. We don't have to go into these details. I'm going to cover a few of these concepts in this lecture, and then we'll be digging into them in detail in future in future lectures. So, but here's kind of an architecture of what it looks like. These are neurons, and these are different layers within the network itself, and these are the potential training classes. And the word class is important, so there's different number of classes that are here. Inception version 3 is one of these models that is public domain that you can download, and ImageNet is another one of those. So they use kind of a combination of these two models and use the transfer learning technique, which means that they added on some of their own modeling to the existing models. And what's amazing about this, and let me step back and say that this is probably a good time to define artificial intelligence versus machine learning versus deep learning, is that you see these terms used quite often, and I use them interchangeably, but really deep learning is really a subset of AI and machine learning, where you're using computations of the multi-layer neural networks like the one above, and using large sets of data, in this case 100,000 images or more. And the more data that you have, and the more complex or more layers that you have in the model, the more accuracy and benefit you can get from the model. And machine learning, you can think of machine learning as, I think, even multiple regression problem as a machine learning application, right? Where you're just using computational statistic techniques to make a prediction. Where deep learning is really about using multiple layers of neural networks within a neural network, and using lots of data to solve a problem. And the more data, the more accurate your solution is. So with that said, something to realize is this is a deep learning application. It's using convolutional neural networks, and where more data that we have, the more accuracy, the better the true positives that we can detect, and minimize the false positives over time. And we'll talk about that in a way, and tools to be able to improve your model. And how would you do that? So here's one simple tool that we'll use in the class called a confusion matrix. So this is the convolutional neural network, and this is the dermatologist. This is the predicted label being, okay, it was a malignancy or benign, and it had, in this case, 9 different prediction classes. And then this is what the true label was. And you can see, okay, if I predicted it to be prediction label 1, the CNN versus the true label 1, we had a very high score here, where the darker color is the higher score. Now you can see the distribution of where the errors were occurring. So for predicted label 6 and true label 0, there looked to be a challenge with the deep learning model, and dermatologists had that challenge as well. So this is the idea of a confusion matrix. Ultimately, validated with a few classes, the accuracy of this particular model was better than the doctors. For 9 classes, this example here, slightly better than the doctors. What's amazing to me is that the doctors had a very overall very somewhat low accuracy of 55%. So this is a tool that we'll use, and we'll use basically this idea of how do we train, and then on a set of data, we'll take a percentage of the whole data set. Let's say 70 or 80% of the data set, we'll train on it, and then we'll reserve a set of data to test the algorithm against of data that's never been seen before by the algorithm itself. And so those are some important concepts that we'll do and implement in class. All right, so not only is Google working on this, but there's other people. And here in this example, they've extended the skin lesions to not only look at melanomas and moles, but other types of skin problems such as psoriasis, eczema, and so forth. So the model keeps expanding. And once again, notice that they're using this Inception V4 model that exists, and they're adding to this model called, the technique is called transfer learning. The other thing that they did is they took into account what's called metadata. So what's the age, the gender, what's the location of the particular lesion, and then also, do they have a fever? That's probably more likely that it would be some kind of rash or something like that, as opposed to a melanoma. So how could metadata, other data, be involved and incorporated into the model? So very fast paced. This is just in 2020 that this article was released. So an interesting space for innovation at this point. I believe, especially for dermatological applications, that AI will make a difference in the next 5 years. There'll be an AI product or solution that complements general practitioners and dermatologists in the future. They already use a device called a dermoscope that could be attached to, the optics can be attached to a phone, and can be created into an application. So there will be commercial implementations of this type of system at some point, I do believe. All right, so this definition of deep learning, just a little more details about that. So when we talk about a small neural network, which means you have a few hidden layers in the neural network, and then a large neural network, you have a large set of hidden layers, as well as a large data set. And the Google skin lesion application, skin cancer application, had over 100, nearly 170,000 images. So your data has to be relatively large. I've seen very accurate solutions with a few hundred images, and then for every orientation, for example, within an image, if you think about a dog versus a cat recognition, you have to have just about every breed of the dog and cat, some images of those at multiple dimensions and multiple orientations, different lighting conditions. It becomes a very challenging problem if you think about solving it for all of the scale problems. You know, you can have a small cat in the image or a large cat, as well as all lighting conditions, potential occlusions of the cat itself. Maybe you don't see the whole cat. So solving that type of problem is a deep learning problem where you really use large data sets to solve the problem. So yeah, a little bit of an error here that should say large number of hidden layers and a large data set. Okay, so what's nice about deep learning is that you can scale the performance, the accuracy, as a function of the data. So the more data that we throw at it, it automatically does the feature extraction and classification and can identify whether this is a car or not a car. Where in machine learning, if you're using a technique like support vector machine or multiple linear regression, you're doing a lot of the feature extraction. The human is doing that, and then machine learning algorithm is doing the classification, and you have the output. So that is a key difference between deep learning and other types of machine learning algorithms. All right, an important point for you to appreciate is the tools have reached a point where they've been abstracted. And in this case, the tools that we're going to be using are TensorFlow and Keras. And so Keras is an API, application programming interface, for deep learning that sits on top of TensorFlow. TensorFlow does all the low-level numerical methods and calculations, and Keras makes using TensorFlow very simple. Also, TensorFlow can be deployed on a GPU, like NVIDIA's GPUs, or Google Colab's, which is a server-based GPU, or desktop GPU, or CPUs. So TensorFlow has ability to deploy to these different computing architectures and platforms. Important thing for you to realize here, and we're going to learn this in class in the first examples, is there's only 6 really lines of code to create a machine learning or deep learning model. Import the right modules into Python. We do the training, set up your training and test data sets, define the model. Here's what the architecture looks like. In this case, we're using just a flat layer of neurons, and then we're flattening that out, and then we use a dense layer of 128 neurons and a dense output of 10. And so this is for the handwriting problem, so we have a 10 outputs, 0 to 9. Here's 5, we have a neural network, and then outputs, and we can get, I've seen better than 90% confidence on a very simple model. And then ultimately we compile it, we fit the model, and then now we're ready to test and evaluate and make predictions. The 7th step is that you can save the model, and saves all the weights, and these weights can be very large. I think the cancer application was the weights for the system, counting all the neurons and the hidden layers, was about 100 megabytes. So I don't recall how big the MNIST model is here. This is the MNIST data set. So this is the handwritten data set from 0 to 9. There's 70,000 images in it. And this is the type of program that you'll be developing. Pretty high level, 6 steps. So do you need to be a programming expert? No. I think you need to be very dangerous on how to use Python and Jupyter Notebooks for this class. And you'll spend most of your time in transforming, setting up the data, and then creating the model. And we'll talk about different techniques for creating your model in this class. Okay. So those are important concepts. I have also included in the class what I call code along videos, where I will step you through how to build the Jupyter Notebook using Keras and TensorFlow, using those 6 steps. And this will be a gentle review back into knowing Python. And so I would ask you to follow along those videos, do the coding so that you come up to speed, and we get you through the Bloom's learning taxonomy, those first 3 steps, fairly quickly. So the first 2 or 3 weeks, I'll be having some of these code along videos and extra videos that you can reference so that you can develop your coding skills and get back into Python very quickly. Okay, so really if I was to abstract TensorFlow into one slide, it's a deep learning library. It's open source, built upon Python, really developed by Google and the community. There's hundreds of thousands now probably of GitHub stars or forks and ability to download the code and modify it. Keras is part of the ecosystem. It sits on top of TensorFlow. And then what we will do is use Keras as our high-level API. We also will use Google Colab, and Google Colab is a GPU in the cloud. And then we will use TensorBoard for visualization of the neural net, and as well as some things like the confusion matrix and convergence of your accuracy and loss functions. All of this is the high level point here is the software. The low level software now has been abstracted, so really domain experts, biomedical engineers, domain experts in many different industries can develop applications fairly quickly and test them and validate them. So that's the era that we're in today, is narrow AI. All right, I'm going to stop here, and then I'm going to record another video for some other concepts, introductory concepts, before we go into super detail on each of these specific areas. So until next time.